Welcome back. In the last one or two classes, we have been trying to understand some of the basic concepts involving spin physics, which are essential to get into more understanding of one and two dimensional NMR spectroscopy. So, as a consequence, we were trying to understand many things. In the last class, we came to the level of understanding interaction of the magnetic moment with an external magnetic field, mu. So we found out the energy of interaction E is equal to minus into minus mu dot B. Both mu and B are vectors. This is total interaction energy. Also, we discussed, remember, this was interaction energy was negative. Why it was negative? Because we said it is to ensure that spins oriented in the direction of the external magnetic field here has lower energy than opposite to that. That is only the concept. As a consequence, negative sign was incorporated into this equation. Now, this was the general expression for the interaction energy, but I also said the interaction energy of the magnetic moment, which is in the opposite direction of the magnetic field, in the opposite direction, they are different. That's what we said in the previous class. This results in different energy states which get separated out in the magnetic field. This is called removal of degeneracy. Remember, I discussed in the last class, energy states are degenerate in the absence of the magnetic field. But in the presence of the magnetic field, the energy state corresponding to these two orientations in the direction of the field, in the direction opposite to the field, are getting separated out. And also, I said these two have different energies. Interaction energy with the magnetic field for magnetic moment in this direction and for the magnetic moment in the opposite direction with the magnetic field, they are different. So now we will work out the interaction energy for each direction of orientation, for each component of mu. Okay, but before that, let us see, as I said, mu is a vector, B is a vector. Of course, that is B naught is a static magnetic field. Main external magnetic field, I said, is always referred to as B naught. Okay, that's the important thing. And this being a vector, we can resolve this into three components. And it is a dot product. So it can be, you can write this as mu x bx plus mu y by plus mu z bz. I'm resolving these vectors. And magnetic field is assumed to be along z axis. We always take the direction of the magnetic field is z axis. Okay. So when I resolve these things, then I consider only the direction of quantization, that is mu z, with the z direction of the magnetic field. So I will consider only mu z and bz. As a consequence, these two terms gets eliminated. These two terms get eliminated. We don't consider that at all. You understand? This is the total energy of interaction. We resolve them into three components each. Took the dot product of that, expanded like this. Now I am telling magnetic field is assumed to be along z-axis. As a consequence, I don't consider x and y components. They get eliminated. Then we are left with only E equal to minus mu z b naught, not b naught. That's wrong. It should be bz. Okay. Now, this interaction, what we do, we know what is mu z. Substitute mu z, which we know what is mu z. Mu is equal to gamma into m into h cross. That is now well known. In the previous, one of the slides in the previous classes, I showed you. Substitute for mu z. This becomes minus m h cross b naught, which I can consider as, of course, I'm considering this as only b naught, but it should be bz, doesn't matter. B naught is assumed to be along z axis. Now E is equal to mh cross omega naught. What is h cross omega naught? Now omega is equal to minus gamma into b naught. This term I'm resolving it. I'm separating out these two terms. Mh cross I'm retaining. Minus gamma b naught, I call it as omega naught. So the energy of interaction of this one, we can bring it to this form, m h cross omega naught. Okay. Now we will resolve them into two components. Energy for the two states alpha and beta, that is plus of state and minus of state, that is alpha beta states. Just find out what is m here. M is equal to plus of and minus of. Substitute for that. For half state minus of, remember there's a minus here. Okay. So, oh sorry, minus component is removed. E alpha and E beta, there is one mistake I have made. This is minus, this is plus, because E alpha is equal to this plus of state. E alpha is equal to half into gamma h b naught or 2 pi. What I did is, it was h cross. Remember in the previous equation, it was h cross. H cross is written as h over 2 pi. H is a Planck's constant. Same way, energy for the beta state is written like this. Okay. Okay. What is happening is, this energy of interaction for these two states, energy is always negative here. As a consequence, plus half appears with a minus sign. Minus half for the beta appears as a positive sign. As a consequence, notice the energy of beta state is more than alpha state. Although we say alpha state is here and beta state is here. M half as a, for alpha state, for m half, it is like this. And for beta state, it is like this. Okay. Alpha and beta orientation of the spin in the direction of the field, in the opposite direction of the field. For m of m equal to half and m equal to minus half are given like this. But in the presence of the magnetic field, this gets interchanged like this because of the negative sign. So beta is appearing to be with the higher energy, alpha is the lower energy. As a consequence, plus half and minus half, because of already there is a negative sign, is equal to E equal to minus mu dot B naught. This appears like this. So in all the books you can find out beta state is written up, that is m equal to minus half state. And alpha state is written with the lower energy like this. Okay. So this is the alpha state is the lower energy, this is a beta state is the higher energy. Although it is written like this, because of the negative sign, it happens like this. Notice this change. In most of the books they write beta as higher energy state, alpha is the low energy state like this. Now, what is the energy difference between alpha and beta state? Take the difference between these two. Difference between these two. Half minus half is 1, or minus half plus half, if you take either of them, depending on alpha beta or beta alpha, doesn't matter. We take delta E, one of them, one direct. Then it turns out to be half gets cancelled out here. You get gamma h b naught over 2 pi. That is the energy difference. It is called delta E. The energy difference between alpha and beta spin states is simply this equation. I am taking the difference, that's all. E alpha, E beta difference is delta E, and that's what I am getting it. Now, you also know from your basic atomic physics, we have studied long back, energy can be expressed as frequency. Delta E is equal to h nu. Remember, long back we would have studied some conversion of energy to frequency, etc. So delta E is equal to h nu. Now equate these two equations, this and this, because both are delta E. Then what will happen? You bring this will to this. H nu is equal to gamma h b naught over 2 pi. What is going to happen now? What is going to happen? This h and this h get cancel out. Because you're equating these two, this is a common factor, gets cancelled out. Then what you are left with nu, which is equal to gamma b naught over 2 pi. Remember, this is the basic equation, very, very important. Don't forget this. I am equating energy separation of alpha and beta state which we calculated based on the interaction, equated this to the frequency to convert into frequency. Now I know when the energy difference when expressed in frequency turns out to be nu is equal to gamma into B naught over 2 pi. This condition is called resonance condition. This is a resonance condition, very important condition. You require this very often in NMR. And this is the equation which has given several Nobel Prizes for NMR spectroscopy who are pioneers. Okay. What do you understand further from this equation? This is a resonance equation. And here gamma is a constant for a given nuclei. 2 is a constant. Pi is a constant. What is different? Only B naught. B naught is a magnetic field. That is not constant. I can vary. Strength of magnetic field is in my hands. I can keep on increasing the magnetic field. I can increase or decrease. I can change it. As a consequence, nu changes linearly because all are constants. Resonance frequencies vary linearly with the magnetic field. Understand? Now I'll double the magnetic field. Let us say at a magnetic field of 4 Tesla, resonating frequency is some frequency. That is a frequency nu. I double the magnetic field to 8 Tesla. The frequency will be 2 nu. So it linearly changes. Resonating frequency depends on the magnetic field, which has a linear dependence. So this explains this diagram, this figure. What happens as a function of increasing the magnetic field? Look at this one. Magnetic field keeps on increasing in this direction. As the magnetic field increases, look at the color is getting changed. From low frequency, it is going to higher frequency region. That means higher the resonating frequency, resonance condition in that nu is increasing. You are getting higher and higher resonating frequency. As the magnetic field increasing, resonating frequency also keeps on increasing. Another thing, if you notice, the size of the arrows. Arrow's thickness is also increasing when the magnetic field changes. What does it mean? There is some more meaning in that. What it means is the sensitivity of detection also is more. As the magnetic field goes up, the signal which is weak becomes more sensitive here. You get more signal. Okay, the magnetic field you are increasing, lines of force is increasing. And now the resonating frequency increases and also the sensitivity will go up. Okay, this is the diagram which energy level separation tells you what happened to two spin states. I'm taking an example of spin half nuclei. When I double the magnetic field, these are the two energy states. Alpha, this is a alpha state. This is a beta spin state. This separation, we calculated the energy for this magnetic field of 4.7 Tesla. It put it into that equation. Nu is equal to gamma into B naught over 2 pi. B naught is 4.7 Tesla. Gamma is known. 2 pi is known. You calculate. Delta E turns out to be 200 megahertz in a magnetic field of 4.7 Tesla. Now here we have doubled it. What is happening? Energy separation also doubled because it is linearly varying. Magnetic frequency linearly varies with the magnetic field. As a consequence, energy levels also have to go increase energy separation. Otherwise, frequency will not increase, right? So this drawing tells you as you increase the energy magnetic field, energy separation between two alpha and beta states have increased linearly. If you change linearly, it is changing linearly. At the two places we saw it is doubled, energy level exactly get doubled, and this is the resonating frequency, which is 400 megahertz, which was 200 here. When you change the magnetic field from 4.7 to 9.4, the resonating frequency from 200 megahertz became 400 megahertz for protons. So what do you understand from this? Higher the magnetic field, we have better resolution and increased sensitivity. We talk more about resolution and sensitivity as we go ahead. But this point has to be clear for you. Higher the magnetic field, higher the resolution and higher the sensitivity. Okay. This table gives you a feel for what is happening when I increase the magnetic field. How the resonating frequency is changing. Look at it. We will concentrate on this magnetic field. This is approximately 4.7 Tesla. Resonating frequency is 200 megahertz. I go to double. I'll go to 9.4. Resonating frequency get doubled. I go double of this. I'll make it 18.8. Look, it goes to 800 megahertz. It is, as you keep increasing the magnetic field, it is linearly changing. The resonating frequency is linearly changing. So this is an important concept you must remember. And B naught, magnetic field, is always expressed in Tesla in NMR. And resonating frequency is always expressed in megahertz. Okay. Okay, with this, we have understood all about resonance in the sense what is the resonance condition, everything. We can even calculate the frequency. We know delta E, that we know nu is equal to gamma into B naught over 2 pi. We know what is B naught, what is gamma, what is 2 and pi. We get the resonating frequency. Now, remember in the very first class, when I showed the electromagnetic spectrum, I said NMR appears in the radio frequency region. I suppose you remember all these points. Am I right? Now let us understand. We'll find out where does NMR spectroscopy, or where does the frequency, if I calculate for a different magnetic field, where does it appear? We will do that. Okay, we'll calculate the resonant frequency of proton using this resonance condition. Of course, I have been telling you the gamma of proton is 26.75 into the 10 to the power 7 radians per Tesla per second. Now I am taking magnetic field as 2.35 Tesla. This is in Tesla. This gamma is in this unit. I know 2, I know pi. Okay, 3.142 pi expressed in radians, 3.151415926. That value you should not forget. That should be in your fingertip always. Substitute all these values. Okay, nu is gamma I know 2, I know pi, this thing, I know magnetic field Tesla. These are simple numbers. Just plug it into your calculator and it turns out to be nu is equal to 100.06 megahertz. I calculated mu is 100.06 megahertz. Okay. We'll do one more experiment, one more calculation. What happens? I change the magnetic field to different value. Now I take magnetic field of 14.1 Tesla. Earlier was 2.35. I changed it to 14.1 Tesla. All other factors remain same, but I am not touching. It has to be same. Plug in the values. Only this number is changed now. That's all. This all remained same. Find out the value. It is 600.36 megahertz. What happened? I changed the magnetic field 6 times. Resonating frequency changed to 6 times. That's okay. This is for proton. Both the resonating frequency of the proton in both the magnetic fields, I took example for calculation, they appeared in megahertz frequency range, 100 and 600. Doesn't matter some number, it is all in the megahertz range. That's fine. What about other nuclei? Let us take the example of carbon 13. Carbon 13 gamma is this. In the same magnetic field 2.35 Tesla, this plug in the value, it turns out to be 25.15 megahertz. Gamma of carbon is 4 times less than that of proton. As a consequence, nu is 4 times less. Correct. Proton was 100.06 or something we worked out, and carbon resonating frequency in the same magnetic field is 25.15 megahertz. Good. Let us see what happens with the other magnetic field which we calculated for proton. 14.1 Tesla. Plug it in. For carbon 13 gamma, it turns out to be 150.98. 4 times less than that of proton. In 14.1 Tesla, proton was resonating at 600, carbon is coming at 150. In 2.35, proton was 100, carbon was 25 megahertz, up around that value. Fine. All are in megahertz. That is the general conclusion. All the nuclei we took, the resonating frequency are all within this megahertz range. Anything except one unstable nuclei like tritium, No other nuclei in the periodic table can have resonating frequency more than that of proton. Remember, highest resonating frequency of all the stable isotopes is always proton. That is the one which is highest gamma. In the magnetic field and all other things kept constant, only gamma is changing. That has the highest gamma. So no nuclei in the periodic table can have a resonating frequency higher than that of proton. Okay, with this, and we know it is all in the megahertz range. If protons resonate at 300 megahertz, we can have to do one more calculation. Of course, this is just for you to understand before you go further. Let us say I have given you, somebody has told me there is a magnetic, he got a spectrum in 300 megahertz for proton. What was the magnetic field? Of course, you can calculate by this equation. You know this equation, bring B naught this side and calculate, find out what is going to happen. So this is 2 pi goes here, 2 pi nu or gamma. Plug in the values, simple. You find out B naught turns out to be 7.04 Tesla. So remember these things. You need to calculate magnetic field. You can calculate resonating frequency for varieties of nuclei. Fine? Okay. All these things we know. Now, in the practical applications, where we have the magnetic field of the order of few Tesla, 14 Tesla up to 20 Tesla, doesn't matter. We calculate it. Even if I have 24 Tesla, resonating frequency turns out to be close to a gigahertz. That is the NMR frequency. But radio frequency range, if you know the radio frequency in the electromagnetic spectrum, range from 20 kilohertz to several gigahertz. 20 kilohertz to several gigahertz. But NMR spectrum, what we saw is resonance frequency, comes in the radio frequency region, megahertz only. As a consequence, NMR, because we know it is a radio frequency range, is from 20 kilohertz to several gigahertz, and our calculated frequency are all in megahertz. I said NMR is detected in the radio frequency region. Are you all with me? I just wanted to show you, we just calculated the resonating frequency for different nuclei for a set of magnetic fields, and we understood they all come in the megahertz range, megahertz frequency range. But in the electromagnetic spectrum, we know radio frequency ranges are all between 20 kilohertz to several gigahertz. As a consequence, I'll say NMR is always detected in the radio frequency region. There is no doubt about it. That means go to any NMR laboratory, all NMR spectrometers operate at megahertz frequency. You understand? Any NMR laboratory you go, you will see the NMR spectrometer is always mentioned in megahertz. For example, go there. Go to any NMR lab. In our lab, we have many spectrometers. You can see it is written 300, 400, 500, 600, 700, 900. Varieties of magnets are there. What do this number refers? These numbers tell you the corresponding resonating frequency of proton in these magnetic fields. In this magnetic field, whose magnetic field can be expressed in some Tesla. If you take the proton NMR, it comes at 500 megahertz. Similarly, in this spectrometer, proton resonated 900 megahertz. That means the magnetic field from here to here is 3 times larger. If this magnetic field is, let us say 7 Tesla, this is 21 Tesla, 3 times larger. So that's what. But what I am trying to tell you is, whatever the number you see on the magnets, if you go to NMR spectrometer, where commercial spectrometers are there with the magnets are there, some numbers are written here. That tells you the corresponding resonating frequency of the spectrometer, and that pertains to resonating frequency of protons. So if I come and tell you I have a 800 megahertz spectrometer, that means I have a magnet written with 800 here, and console everything is matched such that I can protons in that field resonate at 800 megahertz. This is the interpretation you should know. Okay. Now we'll go a little bit more and to understand. We have spin half nuclei where Charge distribution is always spherical. Spin of nuclei. It is a dipole. Okay. Charge nuclei is always spherical. And their behavior is easy to understand. Always in NMR, if I take spin half nuclei, I can understand their behavior, their interaction with magnetic field, etc., among themselves, everything. Very easy to understand. Compared to spin greater than half. Not that we can't understand, but easiness of understanding is better for spin half nuclei. Okay. So spin half nuclei are called dipoles. Why is it a dipole? It's tiny magnet with two poles, like north and south pole. So spin half nuclei is always called a dipole. Spin greater than half do not have spherical charge distribution. The charge distribution has a different shape like this, like a spheroid, like a ellipsoid. The charges are distributed differently. See, here is plus, plus, minus, minus. Whereas in the previous example, you see only two charges, plus if you say this is plus, this is minus. This is plus, this is minus. So only two poles are there. But here, there are four poles, two plus positive charges, poles for two positive charges, two poles for negative charges. That is why it is called quadrupole. Any nuclei with spin greater than half have non-spherical charge distribution, and such nuclei are called quadrupolar nuclei. And such nuclei have what is called electric quadrupole moment. Electric quadrupole moment. Remember, in NMR, as we go ahead in the subsequent classes, we understand a lot more interactions. So far, we are discussing only external interaction, interaction of the nuclear spins with the magnetic field. We have many more interactions, internal. One such is a quadrupolar interaction. All interactions in NMR, except quadrupolar interaction, are magnetic interaction. Only quadrupolar interaction is electric in nature. Please remember, quadrupolar interaction in NMR is electric in nature. All other interactions are magnetic in nature. Okay. Now, I'll try to give you some classical analogy. So far, we are discussing some energy level and spin, etc., in some quantum mechanical concept with the physics terms, without using mathematics or anything. These were the things which were taught for us when we were students with some classical analogy. It holds good to some broadly to a large extent. This classical analogy also holds good. Okay, we'll try to understand this. What will happen? Consider spins in a magnetic field. I consider spin of nuclei. Now, in the absence of the magnetic field, spins are randomly oriented. Random distribution is there. There is no preferred orientation. Now, as soon as you put the sample in a magnetic field which is non-zero, some magnetic field of some Tesla, look at this, what is happening? The random distribution of the spins change to preferred orientations like this. Either they orient up or down, orient in the direction of the field or in the direction opposite to that of the field. Okay, there are only two possibilities. But remember, it can have various possibility orientation, but preferably we have always said there are many nuclear spin. They orient like this and like this, both of them having different orientation, making a preferred angle. We also calculate everything. Okay, so some of them line up in the direction parallel to the field, and some of them line up in the direction parallel opposite to the direction of the magnetic field. Okay. Interestingly, more spins are aligned in the direction of the field than opposing it, because that is the lowest energy option. The lowest energy option is more spins are aligned in the direction of the field than opposing it. Please remember my equation. E is equal to mu dot BH. I put my negative signs to ensure that more spins aligned in the direction of the field, which is negative energy, which is the lower energy, preferred orientation. We put the equation in that equation of energy of interaction. I put a negative sign. I asked you why negative. That I explained there. This is the reason. More spins are aligned in the direction of the field than opposing it, because this is the lowest energy option. Now what happens? Let us understand. Larmor precision. The spin of nuclear are constrained to adapt two possible orientations in the external field given by 2I plus 1. But we know what is the magnetic moment direction. Although we say in the direction of the field, in the direction opposite to the field, we also know what is the angle of orientation. Angle, when the quantization directions we calculated also, right? If our spin half and minus half, which is 54.7, you remember we calculated in one of the previous classes. So two orientations, one 54-degree direction, 54.7 in this direction of the field, one minus 54.7, otherwise 54.7 in the minus direction. We got this. Magnetic moment, we calculated quantization directions. There are two forces acting on it. One is the large force, magnetic field, because of external interaction. It wants to keep it aligned along it. Other force is a spin angular momentum, which wants to keep it spinning at a restricted orientation, which is known. We can calculate that. So there are two forces acting on it. It's like a tug of war. One wants this side, other wants this side. In the loose way, I'll tell you, one is pulling this way, other is pulling the other way. It is like a tug of war. As a consequence, what happens? The magnetic field exerts a torque inducing motion into the magnetic moment. That is, for the spins, it introduces a sort of a torque inducing motion. What will happen? This torque will make the nuclear spins start processing in the along the direction of the magnetic field. This is the magnetic field. It was like this. It was somewhere like this. Two orientation. But some main magnetic field starts pulling, let's say. But the preferred orientation according to quantum mechanics is like this, restricted orientation. As a consequence, what happened? The spins exert a torque, magnetic field, because it is exerting a torque on the spin, they start rotating in a cone in the direction of the magnetic field. But if one spin is rotating like this in the opposite direction of the field, there are millions of nuclear spins, tiny magnets or magnetic moments. They all present in the sample, undergo precision simultaneously at the same frequency. Frequency will not change. The precisional frequency, the speed at which they rotate is same. Simultaneously undergo in the direction oriented field, in the direction opposite to field, it appears as if it is forming two cones like this. Alpha and beta components of the magnetic moment aligns in the direction, particular angle in the magnetic field. Because of this torque, they precess in a cone like this. This is an important thing. Remember, classical analogy, in the aligned spins, magnetic moments, start precessing in this direction and this direction, two cones, due to two preferred orientations. Okay? And the torque magnetic field induces on the spins. This is called Larmor precision. This is called Larmor precision. Now you may ask me a question. They are precessing at some speed. What is this precisional frequency? How fast it is precessing? I must calculate, right? I should know. If I say torque is exerted by the field on the spins and they start precessing like this, what is its speed? How fast it is rotating? What is the frequency of precision? I must calculate. That is called Larmor frequency. I'll calculate that in the next class and show you what is the Larmor precision frequency. So I'll stop for the day. Today we have discussed a lot of things about continuing from the spin physics. Now we have got a classical example. We understood about the degeneracy removal of the states and we calculated the energy difference between these two states. We obtained the resonant condition and calculated the frequencies and then showed it is in the radio frequency region for different magnetic fields, different spins resonating frequency, different nuclei, all come in the radio frequency region. In the classical analogy, I said the spins start precessing like a cone like this, and it's called a Larmor precision frequency. So in the next class, this Larmor frequency, everything will discuss and continue further. Okay, we'll continue further in the next class.